In this question, I'm going to answer, how do we go about solving the integer knapsack problem? How do we solve problems like common substring or common subsequence? And the answer is in the same way we solve every dynamic programming problem. Because here's the thing, almost every dynamic programming problem more or less looks the same, and the key to it is the optimal substructure. Once you find the optimal substructure, then you discover there's some overlapping subproblems and use a bottom-up or a top-down approach in order to prevent unnecessary recomputation of those overlapping subproblems. Let me start you off with the problem. Integer knapsack is a problem where we are trying to fill a knapsack with a total maximum capacity. We have objects that have some weight and some value associated with them. The knapsack can only hold a certain total capacity of the weight. We want to pick the objects such that we have the best possible value. And just to show you a sense of what those objects might look like, here we have 5 objects, and you can see they each have a weight and a value. Well, how do we go about solving this? Naively, we might think that we might sort these by value and then go down the value. But you can think that that doesn't quite work. And if we sort these by weight and go down the weight, that's not going to quite work either. A heuristic that we could use, we could compute the ratio of the value by the weight and then try and figure out what the best value per weight ratio we can see is and go through that and then construct the knapsack in that fashion. It looks kind of like this. But the problem is, as we look through this, we can see, the best possible thing I could construct might take into account, for example, this 16 and this 8 and this 8. It may be the case that I need to revisit something. It may be the case that the next element that I see has much greater value than something that I've seen before. So this approach is just not going to work. We can't solve this greedily. This is definitely a non-greedy problem. I might say, let me try and formulate this as a dynamic programming problem. And the way I'm going to do that is think about my optimization. And I could say, well, my optimization function on n is the max value of the items for 1 up to n. Therefore, my case is, for each n, my first case is I either select the item or I don't select the item or I select the item. If I don't select the item, then my optimization is just everything not including that item. But if I select the item, the problem here is I've lost the ability to revisit things. This is a false start, and it's a false start because what I'm really looking for is I'm looking for some optimal formulation that allows me to maximize, making a subsequent choice. And so the proper formulation for this integer knapsack is as follows. I'm going to define my optimization as the max value of the items from 1 to n given a particular weight limit. Then what I can do is I can say in the case where I don't choose something, then my optimum here is just the same weight limit, but considering 1 fewer item. If I do choose the item, then my optimum is whatever the value of that item was, plus whatever the optimum was for everything not considering that item with a lowered weight. And I want to maximize over these for every single choice, and that gives me my dynamic programming problem. And it's critical that I have to be able to update the weight limit. And so the false start here is in part because I'm not really considering what I need in order to be able to revisit, to prune that combinatoric expansion, or to be able to make a choice there. Well, I can formulate this almost directly off of that formulation. Here you can see, here are the base cases. And the base case is I can't take that item at all, which kind of forces me in one direction. And here's my choice. Either I accept the item, in which case I have my optimum of don't consider that item, or everything but that item with that weight, that item's weight removed from my capacity and the item being marked as taken, or I decline to take that item, in which case I consider the original weight, the original capacity, with every item but the one that I'm looking at with the items that I've taken unchanged. And I just maximize over those. There we go. And as we think about this, what I'm doing here on each step is I'm splaying out between these two choices, and each one of these is recursively splaying out between this choice. This is a recursive formulation. But I am repeatedly solving the same problem. In fact, if I even put a print here and I look at that, I may even see the same problem being solved over and over and over. I'm solving the problem with this particular item, IBBA, with a weight of 1, and here I solved it again. Overlapping subproblems. If I want to solve those overlapping subproblems, well, I can think back to there is always an iterative formulation in order to eliminate this recursion, and it really involves just some sort of data structure. There is always some dynamic programming approach to eliminate the recomputation of these overlapping subproblems, either memoization, the top-down approach, or tabularization, the bottom-up approach. And memoization is so easy, it's not even worth considering. I just stick cache on top of this and I make sure this thing is hashable, and there I'm done. So let's talk about the bottom-up approach. The bottom-up approach is I'm formulating a table. What I'm going to do is I'm going to start from my base case, and I'm going to compute out from that base case out along the frontier. So what I'll do is I'll start with, a table. And this table is going to say, for 0 elements with a weight capacity of W, this is what the maximum value you have is. So for 0 elements, the maximum value, doesn't matter what the weight capacity is, it's always going to be 0. Then I can go through each item, and I can say, for each possible weight capacity from 1 up to whatever the total capacity is, if the item is greater than the weight, then whatever the maximum you could do is just whatever the previous maximum was and not including. This is the do not accept. This is the, I would say, decline step. Or it is the maximum over either you accept the item or you decline the item. Maximizing over what the value would be, it's a maximum of whatever the value would be if you accepted the item or if you declined the item. And here you can see it's considering all of those possible branches, but instead of going top down, it's going bottom up, and it's constructing these as you go. And when we do this, we get the answer that we'd expect, 32. Almost all dynamic programming problems break down in this fashion. I want to show you, just briefly show you the setup for longest common subsequence, and you'll see they all look the same. All dynamic programs look the same. Find the optimal substructure, write that optimization statement, implement it almost directly, and then find the overlapping subproblems and either build the table going up, in which case you have to manage the dependencies, so it's a little bit tricky, or stick a cache decorator, memoize it, and call it a day. Now, between you and me, I think the table formulation is a little bit better because it also corresponds a little bit more to this idea of recursion being undesirable in Python. But for the most part, that's really a mechanical transformative step. Really, the key part to all of this is discovering that optimal substructure, discovering what the optimization statement is. Here is longest common subsequence. I have 2 sequences of elements, A, B, C, D, E, F, and G, and B, C, X, D, X, F, G, and I want to find what is the longest subsequence of items that is common. So here you can see it's going to be B, C, D, F, G. Well, here's my dynamic programming optimization. Either, if there are no elements, if I and J have no elements in them, sorry, let me reformulate this. This here is what is the optimum considering up to index I and index J on the 2 input data sets, which we'll call X's and Y's. So if we're not considering any elements, then it's 0. Like the longest common subsequence that we have, if we consider no elements from the 2 structures, is 0. If we're considering some element, some index of these 2 structures, and that index matches, then the longest common subsequence is just 1 plus whatever matches when we consider the previous ones. And the choice that we make is either we accept, we go forward on the left-hand side, or we go forward on the right-hand side, we accept a character from I, or we accept a character from X's, or we accept a character from Y's, and we just maximize over that. And it turns out that the formulation for this will look almost exactly like this. This here is your base case. This is your recursive step. Add a cache memoize decorator or perform that transformation into that tabular formulation, and you've solved it. That is the idea behind dynamic programming. Now, whether dynamic programming comes up in our work, well, it absolutely does, because a lot of the problems we want to solve are, in fact, scheduling problems. They're, in fact, integer knapsack problems, these kind of optimization problems that we know don't have really nice, log n or constant time or even linear time formulations. We know that there may be some recursive formulation, and there may be some combinatoric expansion, there may be some quadratic, if not factorial time complexity to them. As a consequence of that, what we're going to do is we're going to look for optimal substructure. We're going to look for how we can formulate an optimization statement where that optimization statement encodes what the base cases are and then encodes what the answer to each step of the problem is in terms of other answers to the problem and a maximization, minimization, some sort of optimization over those. Most of the time, we can do this in terms of just like maximization. And then that gives us a recursive formulation almost directly. We encode that, and then we just figure out how to transform that into something that's efficient by either caching or tabularizing, either working bottom up or working top down. Almost every single one of at least the classical problems look exactly this way. There's really not that much variation. Obviously, in the real world, when we talk about these things, we want to implement them. There's quite a bit of underlying variation in making these things actually fast. But the core interview problem is really optimal substructure, overlapping subproblems, formulate an optimization statement, implement it, and then optimize it via a bottom-up or a top-down approach. Like with that said, I feel like, or I hope that you all have a better sense of greedy problems, dynamic programming problems, and also divide and conquer problems, a better sense of recursion, and a better sense of how to tackle these without just saying, oh, there's the trick, let me go find the trick. You have a methodical process. Step one, look for that optimal substructure. In other words, look to define how to get the optimal answer in terms of optimal answers to smaller problems. Formulate that optimization statement that almost directly leads to the recursive formulation of the problem, and then think, I got to make this fast. Do I do a bottom-up approach or a top-down approach? Do I add a caching decorator, or do I build a table as I go up? Sometimes one approach will be easier than the other. Sometimes the other approach might have some additional tricks that you can employ to make it more efficient. But ultimately, it's all pretty much the same stuff. And hopefully, you have a little bit of a leg up the next time you encounter these problems, either in your work or an interview.